If you've been watching our channel, you know we've been following 3IATLAS for months now. Recently, NASA released a new Hubble image of 3IATLAS. At first look, the image seems simple. It shows a tiny point of light surrounded by a smooth blue glow. It almost looks boring. An independent astrophotographer who has been tracking this object night after night says that image does not tell the full story. What Hubble saw, and what the raw data still shows today, looks very different. This video is made possible by Ray's astrophotography. The observations you're about to see come from his careful tracking of 3IATLAS over time. Please check out his channel and support his work. The link is in the description. What Ray noticed in the new Hubble image. When Ray first saw the newly released Hubble image of 3IATLAS, his reaction wasn't excitement or amazement, but confusion. The image showed the object as a very small, sharp point of light, sitting inside a much larger blue coma, clean and compact in a way that immediately felt off to him. At a quick glance, it almost looked like a distant star with a soft glow around it, rather than an active comet-like object. And Ray didn't arrive at that reaction casually. He's been imaging 3IATLAS from the ground again and again, watching how it behaves over time, so when something suddenly looks very different, it stands out. One thing Ray was quick to clarify is what he was not worried about. A lot of people online immediately focused on the hexagonal shapes visible in the Hubble image and started speculating wildly about them. Ray addressed that directly and said those shapes are most likely optical artifacts, caused by the way light passes through Hubble's mirror and support structure. In simple terms, they're quirks of the telescope, not features of the object itself. But that wasn't the issue keeping him up at night. The real problem was much simpler and much harder to ignore. The object itself looked wrong. Ray had never seen 3IATLAS appear as a clean point of light before. Not in his own images. Not in earlier Hubble images. Not in any data he had worked with. So the obvious question forms almost instantly. How did Hubble suddenly capture 3IATLAS as a point source when it never looked that way before? If an object has always looked extended and structured, and then one day it suddenly looks like a dot, wouldn't you want to know why? Of course you would. And Ray did too. He pointed out that in previous images, including older Hubble observations, 3IATLAS appeared much larger and brighter, with visible structure and a clear sense of direction. There was a head and there was material trailing behind it. It looked active and spread out, not compact. So when the new image showed a tight point of light instead, Ray couldn't brush it off. Another important detail here is that Ray wasn't comparing one picture to another in a casual way. He has a running visual memory of this object because he's been tracking it repeatedly. When you observe something night after night, you don't just remember one frame, you remember how it behaves. You remember its shape, its brightness, and how it changes. That's why this stood out to him immediately. It was a clear change in how the object appeared. So Ray asked himself a very grounded question. Is this something new about the object, or is it something about how the image was made? Instead of guessing, Ray chose the most straightforward option available to him. He decided to take a closer look at the released image itself. He zoomed into the JPEG that NASA published and studied it carefully. What he saw only deepened his confusion. The core of the object stayed tight and point-like, even when zoomed in, and much of the surrounding structure he was used to seeing just wasn't there. It wasn't that the image was low quality. It was high quality, polished, and clean. But that cleanliness was part of the problem. So rather than speculating about motives or jumping to dramatic explanations, Ray decided to check whether the published image actually reflected what Hubble recorded. He navigated to the Hubble archive, located the specific observation from December 4, and downloaded the raw files. NASA makes Hubble's observations publicly available through an official archive, which means anyone with the right knowledge and patience can download the original files. And this is where Ray's curiosity turned into something more serious. Because the moment he opened the raw data, even without processing, even without color, the object appeared larger and more extended than what the published image suggested. That alone told him that something important was happening between the raw data stage and the final released image. Because if the raw data shows something larger and more complex, why does the image shown to the world look so simple? What the raw Hubble data shows. Once Ray decided to stop guessing and actually check what Hubble recorded, the very first thing he did was download the raw images taken on December 4. These are the plain, black and white files that come straight from Hubble's sensors, before any heavy cleanup, color choices, or smoothing is applied. In simple terms, this is the closest version of the data you can get to what the telescope actually saw at that moment in space. When he looks at the details of those files, one thing jumps out immediately: the exposure time. Each image was taken with an exposure of about 270 seconds, which is roughly 4.5 minutes. For an object as bright as 3IATLAS, that's a very long exposure. Let me ask you something simple. Have you ever taken a photo of a bright lamp at night and ended up with a big white blob instead of a clear shape? That's what happens when too much light hits the camera. Ray explains that the same thing happens with telescopes. When you expose for too long, bright objects lose detail, edges blur together, and structure turns into smooth glow. We're talking about a basic trade-off here. Long exposures are great for faint objects, but for bright ones, they can actually hide information. Ray points out that earlier images of 3IATLAS used much shorter exposures, sometimes around 40 seconds, and those images showed far more structure and motion. So when he sees 4.5-minute exposures used on a bright, active object, he immediately starts wondering why. Alright, so what does he actually see when he opens the raw files? Well, 3IATLAS does not look like a point of light. Even without any processing, even without color, the object already looks larger and extended. There's a broader core with surrounding material, and it doesn't just collapse into a tiny dot. And this is important, because it tells Ray that the compact point seen in the released image is not coming directly from the raw data. Now Ray doesn't stop there. He starts processing the images himself, step by step. He applies cleanup steps to reduce noise, similar to what NASA does when preparing images for release, essentially trying to see if, by following reasonable steps, he can honestly recreate the image that was shown to the public. And here's where things get interesting again. Even after processing the raw data carefully, Ray still ends up with images that show more structure than the released version. The coma stays larger. The object does not fully shrink into a clean point. The extended features don't disappear the way they do in the public image. So this tells him that the difference isn't just about raw versus processed. It's about how far the processing is pushed, and what assumptions guide it. At this point, Ray introduces a concept called point spread function modeling, or PSF for short. Now don't let the name scare you, because the idea is actually simple. No telescope produces perfect points of light. Light spreads slightly as it passes through mirrors and lenses. PSF modeling is a math-based way to understand that spreading and correct for it, so images look sharper and cleaner. It's a normal tool used all the time in astronomy. But this is the key detail Ray focuses on. PSF modeling assumes that the object you're looking at behaves like a point source, meaning most of its light comes from one small central spot. That assumption works great for stars. But Ray asks a very fair question. What if 3IATLAS is not acting like a simple point source? If the object is actually extended, with real structure and uneven brightness, then applying strong point base sharpening can flatten those features. The software doesn't know what's real and what's not. It only follows the rules it's given. And if the rule says, find the point and sharpen it, the output will move in that direction. So let me put this another way. If you tell the software to look for a dot, should we be surprised when it gives you one? Probably not. And this is why Ray believes PSF modeling likely played a big role in turning an extended object into the compact point seen in the released image. Ray is careful about how he explains this. He doesn't say PSF modeling is fake or dishonest. Instead, it's powerful, and because it's powerful, it needs to be used carefully. Processing choices, far from being neutral, have a key role in shaping what survives and what disappears. When you combine very long exposures with point-based sharpening, the result naturally favors smoothness over complexity. So, if two people start with the same raw data and end up with images that look very different, what caused that difference? It was the choices made during processing. Ray even explains that when he tries to push his own processing further to match the released image exactly, he has to suppress structure that is clearly present in the data. In other words, to get that clean point, he has to remove information. And without a clear scientific reason to do that, he's not comfortable going that far. This is where Ray's concern becomes very clear. The raw Hubble data shows 3I/ATLAS as an extended, bright object. His own processing confirms that. His backyard images support it. And yet the image released to the public presents something much simpler. That doesn't automatically mean anyone is wrong, but it does mean something important is being filtered out. What Ray consistently sees in his own observations. Now this is the part Ray keeps coming back to, because it's the part he trusts the most, his own repeated observations. Night after night, from his backyard, using the same equipment and the same careful approach, 3I/ATLAS keeps showing him the same overall shape. It doesn't matter if the sky conditions change slightly or if he tweaks his processing settings. The object consistently appears with a cone-shaped front, followed by an elongated structure trailing behind it, almost like the object has a clear direction and flow rather than being evenly spread out in all directions. So, if an object keeps showing the same structure across many nights, many images, and many processing attempts, does that sound like an accident? Probably not. And that's exactly why Ray pays so much attention to repeatability. In astronomy, seeing the same thing again and again is one of the strongest signs that what you're seeing is real. Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video for more exciting content.